Good morning. My name is Ez. I know everyone is still grabbing lunch, so I'm gonna go slow. Anyways, I like to kind of like make it as interactive as possible, so we're gonna take a lot of questions. This is a fairly technical talk. It essentially covers how we had a project where we essentially built a bunch of AI models to detect attacks in the multi-cloud chaos. I will speak very little about the chaos, and I will speak a lot more about the actual steps that you guys can take and build very simple AI models that can be very helpful. All right, a little bit about me. My name is Ez. I'm a cyber data scientist. I'm a co-founder of a company called Cypienta, and we're essentially an AI vendor for cybersecurity. So we just make AI models that people can use in their data lake or whatnot, similar to detection as code kind of thing. Before that, I led some data science and threat research efforts in the Royal Bank of Canada, Orange, Huawei, as well as Forescout. And I did some academic work, got a bunch of useless papers and a bunch of useless certificates that just say I passed an exam once. But essentially, this means I'm a nerd. I'm gonna say a bunch of stuff that might not make a lot of sense to you, which is fine. Throw your hand in the air or essentially just write your question somewhere. And I'm happy to take as many questions as possible. The idea is to share our work with the community so that people can start investing a little bit more into developing their own AI in their own SOCs or in their own security organizations, and actually using very, very simple AI models in their everyday workflows without essentially using them as black boxes, like actually building them, because they're not that bad to build. All right, let's talk a little bit about the progression of security attacks. It seems like every time we go through a security attack, at least in my career, we thought it's so bad, but then a few months pass by and we're like, wow, all right, that was not bad. This is terrible. And I think we attribute that mainly as security folks to like our technology complexity growing like exponentially every day kind of thing. So maybe let's do a little bit of a show of hands. I think we have enough people in the room. How many people here have actually been victims of cybersecurity attacks? All right, a bunch of us are ashamed, so that's fine. I mean, I know at least, statistically speaking, at least 70% of the people here have been victims of cybersecurity attacks that they know of, right? So I might be a victim of cyber attack that I don't know of, right? You might find my name on a leaked database somewhere and I messed up, I didn't change that password, boom, I'm part of a security breach and I don't even know it because you didn't do much with that account yet. So yeah, I mean, I remember my first one was when I was 13 and I got hacked with a Trojan. So someone sent me like a little meme, like I was always a big fan of memes and like comics and whatnot. So this person sent me a PNG, and when I clicked on it, I can hear my tiny laptop's fan going like crazy, right? And I knew like some shit is going up. So I was like, ah man, like, and I turned off my laptop and I was like, kind of like obsessing over this for a while. But what I learned from that experience is throughout my career, I would always like expect the worst. And it seems like the Trojan was no more the problem. There were like a lot more attack vectors. So many threat vectors are evolving every day. And attackers really came a long way. Like that was a script kiddie back then and they just used a Trojan. Script kiddies today use like social engineering toolkits on Kali and to kind of like better credential harvest your stuff. And they use like Metasploit easily with Armitage or whatnot. So they have really evolved beyond measure in how easy it is to actually attack a system as a script kiddie. You don't really have to go through like years of education to do any of that. But anyways, speaking of how attacks have grown beyond measure, according to Mandiant, attacks today are actually so stealthy, only 9% ever do generate an alert. Yet on average, your security teams are bombarded with more than 10,000 alerts every single day. Not only that, they have up to 130 tools, according to Palo Alto Networks, on average. So there's no doubt that we have some interesting effectiveness here, and we're pretty bloated when it comes to an industry. While our adversaries don't seem to have that issue. I mean, their tools are pretty lean. You can very easily get the tools for offensive security. You can kind of like run a whole offensive security team with like a handful of tools, and you can be like pretty dangerous. But we know the saying, you have to mess up once on the defense. Offense is a lot easier. So the theory is our systems today are less secure than they were 50 years ago, right? And that doesn't sit very well until you think about how simple your own home was 50 years ago, right? It was very simple. It was a linear network. Today, it's mayhem. You got IoT, you're working from home, you got, I don't know how many cloud subscriptions you're paying to, you got like your own crypto wallets or you're mining or whatnot, you got all kinds of crazy stuff. At your home network, it's actually a lot easier to hack your 13-year-old than it was to hack me as a 13-year-old about 20 years ago or 10 years ago. I'm not that old, 10 years ago. But yeah, even our critical infrastructure, it used to be air-gapped. Like I remember I did like a little internship, and our critical infrastructure was actually completely air-gapped. Like there was like very few attack pathways. And I know that many of you know how Stuxnet got hacked. The attack pathways were so limited that they had to deploy the virus all over the world and hope that one day that virus would make it in a USB to one of the reactor systems. Today, it's not that hard anymore. Our grid is so technologically complicated, essentially leaving so many attack surfaces to the attackers. You can probably show Dan a bunch of IPs that are related to a critical infrastructure somewhere around the world. So what that means is essentially your security people are always stressed and are running at an evolving disadvantage, right? Their systems are getting more complicated, which means it's actually harder to find attacks in the noise. It's way harder to find the needles in the haystack, and the haystack keeps on getting bigger, while the needles keep on getting tinier. So anyways, these security people, including yourselves, have always been yelling about the lack of correlation of seemingly disparate events. How do we know that things are connected? How do we know that this is an attack, not a false positive? How do we know that this is an attack, not a one-off? How do we know that these series of events constitute an attack and are not just a random probability that looks like an attack sequence? And when we look at what we currently do, we seem like we're doing enough. I mean, we're already collecting every single sensor alert, event, telemetry, whatever, right? Like we're collecting all kinds of CCTV cameras, smart locks, we're collecting VPN logs, proxy logs, web gateways, email security, all kinds of stuff. Endpoint network, you guys are paying incredible security budgets, and hopefully these solutions are well configured that they're actually pulling enough data for you. And your security teams are probably aggregating them in some sort of security data lake or a SIM or whatnot. And then you have your own logic to kind of like also query for these sequences of interesting events. However, the logic is highly deterministic. So this is a well-known, for instance, format called the Sigma format. Essentially, this says, look for, in this specific case, look for commands in a web request, for instance. So you're looking for specific fields and specific values, and ideally you find something along these lines deterministically, right? So think about it like Yara rules in antiviruses, right? Like back in the day, McAfee had like some proper Yara rules and everyone was using McAfee. Today, EDRs are more based on like probabilistic detection. So you're looking for like an AI that can find weird anomalies in your system execution and whatnot. So we're kind of still there in the deterministic logic to find sequences that are interesting. And Sigma is doing pretty well for itself, actually. So Sigma is a open source community that essentially commoditized all threat detection. So Splunk commoditized everything. Microsoft's commoditized their threat packs as well. So you can just go on Sigma and find a lot of threat packs. And the reason is, in deterministic logic, it's highly based on threat intelligence. So it's highly based on figuring out what are the right fields am I searching for today. And instead of hiring everyone in the world, I can be like, guys, let's just work on this together, okay? When you see something, contribute it. When I see something, contribute it, right? So threat intelligence, because we're looking for very, very specific, narrow, high precision logic. The more, the merrier. When you move a little bit into rule sets and detection packs, you find that a lot of them try to get MITRE ATT&CK techniques. Most of them fail. Most of them don't have MITRE ATT&CK techniques. And the ones that do are not usually high quality. But there is a movement to get more MITRE ATT&CK techniques in your detection. And a good reason for that is, if you don't know, MITRE ATT&CK techniques are an abstraction. So instead of saying that this is an alert that would trigger on the text that says I'm an African prince that will give you $1 million if you send me a $50 iTunes gift card, I can just say, okay, this alert is mapped to phishing, which is a tactic known as initial access, and you immediately have it in the right context in your brain. What is the right mitigation? What's the right detection? What do I do? What are the guidelines, right? So it's a very cool abstraction of attacks. And the most important piece is actually it maps you to the adversary's goals. So similar to a marketing funnel or whatever, you have an actual kill chain. And you guys are all familiar with this. So a cyber kill chain would essentially go from the left to the right, from initial access all the way through lateral movement, exfiltration, and then some sort of impact as well. So obviously, MITRE ATT&CK is a treasure trove. You have a lot of detection, mitigation guidelines, and that usually that tag would help you with consistency. Your security people, they're not all consistent, and they come from different backgrounds. They come from different walks of life. They might not know how to essentially hunt a certain threat. You're trying to give them some sort of a guideline. So MITRE ATT&CK is amazing for that in terms of techniques. However, attacks usually look something like this. So they usually look like a bunch of events. You never get a full attack that took down, let's say, Equifax, right? That was not a single email. That was not a single exploit. That was not a single technique. It's never a single technique. Any of the attacks that hacked or breached any of us, including when I was a little kid, it actually covered pretty much all of these. Like that little Trojan had techniques that cover all of these, right? Like I had the drive-by, I had a downloader for privilege escalation. It entered registry keys into my thing. It had command and control on a certain port on TCP. It did some sort of exfiltration. It was like retrieving files and like webcam pictures and stuff like that. So it had all kinds of stuff, right? And the response to that was the abstraction of what MITRE calls the attack flow. So if you guys are not familiar with what is an attack flow, it's a MITRE project similar to MITRE ATT&CK. However, this one is based on looking for causal sequences of techniques. Techniques that happens in certain orders. And when they happen in certain orders, we know that, you know what, that's the specific software. That's the specific playbook of this attacker. So maybe this APT that runs in Latin America and targets mainly, let's say, the Middle East or whatnot, they usually do it this way. They usually have a playbook. They might have automated it. They might have trained their people on it. But that's usually what they do. They go in here and they look for these specific exploits. They scan for these specific targets because they have their own 0 days in these specific areas. That's usually their pathway. So attack flow does that in terms of mapping well-known attack flows or well-known kill chains that we have seen before. And you can easily look for that as well. And these were all answers to the biggest problem that your security people were talking about, the lack of correlation. How do we correlate stuff? Attack flow came up with more deterministic logic. You essentially connect the stuff that we know happened before in a specific sequence. Only problem with that is you have so many possible sequences. So this is not exactly a problem for deterministic logic. This makes a lot more sense for probabilistic, essentially, solutions. And in this day and age, you got to use a little bit of probabilistic stuff because your interns and your researchers and whatnot really want to build that little AI, and they want to be proud of it. So I will walk you through that in a bit. What we try to do is we essentially say, OK, the biggest problem is essentially correlating data and finding attacks, yada, yada, yada. Why not? So sure. What's the step one? Do essentially what Sigma tried to do, find attack techniques for everything. Cool, okay. Some vendors try to do that, but at the end of the day, when you look at all of your alerts, attack techniques are coming from different authors, not consistent, kind of low quality, assuming you find them in all of your data types and all of your vendors, and you will not. So first one, let's make a model that just gives you proper MITRE attack techniques for every alert. Step two, let's make another model that would essentially take a bunch of alerts, and these alerts are going to have attack techniques, and finds probabilistic sequences that would actually make sense as causal kill chains. All right, let's get to building. We put our data science hats on, and we get to the fun part. So how do I get the relevant MITRE attack technique and tactic for all of my events? That kind of sounds like a classification model. So just look at the text. And similar to our classification model that would look at a picture of a dog and say that's a dog, I would look at essentially a text for, let's say, a denial of service, and I would be like, that's a denial of service. So how do we do that? Because it's 2023, if I don't have an LLM on a slide, people start throwing tomatoes at me. So we definitely got the biggest freaking LLM. Why not, right? And Canada was nice enough to give us access to a supercomputer, because that's very expensive to train. So we had a supercomputer to play with, and we were like, OK, what should we do with that LLM? That LLM doesn't know anything. We can make it know English, like ChatGPT. We can make it read a bunch of English literature and English Reddit threads, and it would be really good at English. Or instead of that, we don't make a generic purpose AI. We actually train it from scratch on cybersecurity. It's a nerd model that cannot speak English. It can only speak cybersecurity stuff. So how do we do that? We downloaded every single possible cybersecurity research paper, every single possible cybersecurity lecture note, every single possible cybersecurity thread on Stack Overflow or Reddit, every single cybersecurity discussion, every single cybersecurity book that was cheap enough to buy the copyrights for, because these are expensive. And then we give all of that to an LLM so that essentially it trains what we call a word embedding. That's fancy words for essentially saying that it knows that malware is closer to virus than malware is to UDP or TCP. Essentially, what is the distance between words? So we know in English, he and she and whatnot are pronouns, so they're kind of close, while they're kind of like not as close to, let's say, other words, right? Like it or whatnot, or zero or whatever. So essentially, we get that first part done, and that usually takes a supercomputer, so we're going to make that model essentially available for people to use and build on. And then the next piece is the fine-tuning piece. So when you're doing fine-tuning, you essentially have a downstream task, such as in this case, we have the exact task of find me MITRE attack techniques that match my alert, right? However, when you come to that piece of fine-tuning, you got to find the proper data set. Finding a proper data set is not easy in cybersecurity. Like, I wish this was healthcare, right? Like, people would just like sign off their x-rays. They'd be like, yeah, use it for research. In cybersecurity, people do not share their stuff. We tried actually buying, and we actually did buy a bunch of data sets. They were not good. So what we ended up doing is we actually hired our own security analyst, singular security analyst, to make sure we have good consistency. We bought rule sets and detection packs, and we downloaded all the free ones. And we essentially just made that person sit down for a whole year, and they would just say, you know what, this rule set is this technique. This rule set, this rule is this technique. This alert is this technique, yada, yada, yada. And we essentially like enforce consistency. That's a big one with AI models. Otherwise, they start hallucinating a lot. But essentially, we would make sure that they're fine-tuned on data that is highly consistent. So we made sure like we have lookup tables and all kinds of that, and regular expressions to make sure that they're kind of like consistent from these labels to these other labels and stuff like that. So it was highly a data labeling intensive effort. So when you're engaging on a project like this, make sure you have at least an intern or someone that you would trust on that, and then manage them in terms of consistency. That's a big one. And then once you do that, you can easily pass that data set whenever it's good enough and consistent enough after you check it to the model that already knows cybersecurity, and that model now will get a little bit better at this specific task. But it can do so many tasks, right? But this specific task, it got a little bit better at, and you deploy it. So if you guys are looking to deploy certain models, I highly recommend Amazon SageMaker. This deployment model, you get a container that is local. You do not send your data to anyone. No, don't send it to ChatGPT, please. So yeah, like everything is local. You have it in your own local network in AWS, so you're not sharing it with anyone. And we can start playing with it. And what we see is it's actually pretty okay. Like the first one is actually system binary execution as a technique. Second one is actually phishing, although I literally made up that text. It wasn't even a real alert, so you can see that it's highly customizable. Like when you work with organizations that develop their own sensors, develop their own alerts, you kind of want that customization. So that's pretty cool. Like it just took any kind of text and it would work on it. The third and fourth one were actually pretty hard. Like it took me a while to figure out why was it this way. But yeah, the third one is drive-by compromise, and the fourth one is account manipulation. Yeah. So it was pretty impressive. So we move on, right? That was an easy and nice task. You guys can probably replicate that. We'll help you do that. And then the second step was a little bit more tricky. So the second step was essentially finding alerts that, number one, are highly related. Number two, they should also be a little bit causal. So let's dissect that. What is related, right? So I was a threat hunter at some point, and in threat hunting, you will essentially take a look at an alert, and you'll be like, okay, how does that alert relate to that other event that we know already happened? Maybe it happened in the same time proximity, happened in the same day. So you look at the time dimension as a query. You start querying for what other events happened in this time bin, right? And then you go in and you query for maybe, you know what, maybe they use the same user credentials. So maybe these two alerts were both coming from this specific SSO account. Or maybe these two alerts were both coming from the HR department, like a user group. So you start looking for joining logic kind of thing. And when I wore the data science hat with my team members, we were like, you know what, why are we still doing investigations in essentially a sequential manner? Why don't we just push every single data point on a big graph and take it from there? And then we can essentially dissect that model into first a clustering model and then a causation model or a sequentialization model. So to do the clustering model, we talked about possible joining logic. They're both coming from the same country. They're both coming from the same IP range. They're both coming from the same operating system. They both involve the same vulnerability, whatever. Why are these hypotheses for investigations? Don't do that. Just put everything, like don't wait until you enrich it with VirusTotal. Enrich everything with VirusTotal and put everything, right? Put everything on a big graph, and you can follow the cyber knowledge graph architecture that was put out by our backers, Oak Ridge National Lab. It's called SciGraph. Amazing work there. And they essentially just help you connect them. And you can do a little bit of feature importance. So what is a little bit more important than others? Like, what do these two alerts share the same IP? Is that slightly more important than them sharing the same time? Maybe for you, maybe not. It's kind of like something to tune. But then, once you have this, every single possible joining logic in a big graph, the next logical step is to essentially do some sort of clustering on top of it to find the highly related groups of alerts or groups of incidents. So what we do is essentially we run it through an embedding algorithm. It's called TGL, so temporal graph learning. And that's a temporal graph that has like temporal dimensions. You essentially take that graph, you generate an embedding, you go through a density-based clustering. These sound very fancy, but they're not. These are literally like one lines of Python code. You don't really have to understand, you have to use them. Kind of like how we don't understand how maybe combustion engines work down to the last bolt in them. We still use combustion engines. So you don't have to be a complete scientist to be able to apply the science. And it's super easy to apply it. And I would encourage you to take the first few steps. Once we have these clusters, so we already have the graph with all the alerts, all the possible joining logic. We essentially convert them into embeddings so that we have dimensions. X, Y, Z kind of dimensions. And then we find those that are kind of close to each other. They might be close based on temporal proximity, IP, whatever. And then we have these clusters. We're like, OK, now what do we do with the whole sequentiality thing? You were talking about causality, sequentiality. How do we model these? There is a neat model called the Markov model. It's stochastic, and you can use the hidden Markov model to allow for essentially looking at past states, not just looking at the current state, so that you can actually base your logic based on a lot more than just the most recent alert. And essentially, you would use that, and it would spit out chains that fit what you define. And in this case, like we defined, you know what, we need at least a bunch of clusters to satisfy a bunch of tactics, and ideally, the distance between them is not too bad. So they have to be closer to the tactics that are sequential. Again, we package that into an AWS SageMaker because that's an amazing way to package things. Super, super easy. Put your stuff on an S3. This becomes an API. Have a Lambda function that essentially just pulls it out of the S3, runs it to the API, and boom, you get a bunch of alert IDs that map to what we call attack flows. So this is actually coming from a public data set. So unlike the first model, where we did not have a public data set, we had to literally create our own data set from scratch. In this one, we actually had a data set from communication security establishments. So CSC, shout out to CSC if you guys are around. You guys are amazing. Thank you so much. You guys make cool data sets. And at this point, I think you have a bunch of data sets with Canadian Institute of Cybersecurity, so a bunch of public data sets that your intern and cyber data scientists can play with, and they can make some pretty cool stuff because they already have the attacks and they're already labeled, right? So you can just be like, detect me these attacks. What we do on this specific data set is we essentially went from all of the alerts to these attack chains. That data set actually only had 2 attack chains. And there were one-to-many and many-to-one. So you can already tell they are the big chains. So they are the chains that had 200 alerts or 200 plus alerts. And then we found some other chains. So we're like, our model is not that good. Let's look into it. And when we looked into it, interestingly, these chains are actually pretty valid. And we dug a little bit into it. We chatted with the authors of the data set. And apparently, there was a misconfigured firewall in the test bed. And they actually got attacks that they didn't know about from the open internet. And that was pretty cool as a finding. We found some pretty cool stuff on private data sets, but it's pretty cool when you find it in a public data set because you can like, just show it to everyone and show it to the authors and to the academic community, and that becomes pretty interesting. But yeah, like there's always some validity, like whatever you play with the hyperparameters. At the end of the day, like you're putting some logic into it. It's not like a black box. So you say, what is the importance? Remember, like what is the importance of the IP connection between 2 alerts? What's the importance of the geolocation of the IP? You kind of set some weights, so you can easily go in and you kind of like edit it. It's not a complete black box. It's pretty easy to play with, and your data scientists will find a lot of arguments in these functions in Python. And they will kind of like have fun tuning them. And it's not that bad to tune as well. These are small models. So you can essentially just run a full tuning function if you have a ground truth labeled data set like this and let it just fit the data set or overfit it or whatever. So you can kind of like play that game pretty interestingly if you take that step. So yeah, these were pretty cool. And they were kind of like interesting findings. But we wanted to wrap up essentially how would these help a team right now kind of thing. And we played around with where would things fit. And we found that I think in general, APIs or machine learning models will probably come after the SIM. They'll probably come after everything you already have. So let's say you have a security data lake or you have somewhere where you run your deterministic logic. Your next generation of security products are probably just going to be like AI models that you develop or you buy from an AI vendor or something. But they will probably come afterwards, all of your stuff. So you'll already have your EDR, you'll already have your deterministic stuff, and then you'd already run your detection as code through Sigma or whatnot, like whatever you use as a SIM rule for correlation. If it's within a SIM, within a secure data lake, it's up to you. But then the APIs would essentially enrich stuff, and they would give you some attack flows, and you can send those back into the SIM as well. It's just an API, so you can really play with it as much as you want. But essentially, to recap, this little blob of models that you can build in about 2 months worth of an internship with any of the cyber data scientists or any of the regular data scientists that Canada pumps out. You can easily get something along these lines done in terms of an API that gets you attack flows. Just give them these ideas, give them these models, and they will go after it, and you can give them my information. I'd be happy to take them through it. These are pretty cool models, and we're going to actually play with them a lot more in the Arsenal. So if you guys are around tomorrow or after, do not miss Arsenal for the world. It's just like a bunch of open tools that people play with. So go in there and check out what the community has developed. But yeah, if you're interested, take a picture of this and show up tomorrow to Arsenal sometime or the day after, and you can poke holes. You can bring your team to kind of like learn how to use those. We have a bunch of models that we also like just give out for free so that people can test and give us some feedback because we're still working on them. We're pretty R&D intensive, so we love feedback. But that's a wrap. There's an L flying out of my LinkedIn handle, but that's fine. So you guys can find me on LinkedIn or email me any questions if you don't have any right now, or you can send them to your technical data science interns. But that's a wrap from me. It was an absolute pleasure chatting with you guys. If you have any questions, please come up. Thank you. All right.
I know I have a question.
Please.
Where's the multi-cloud chaos? I was looking forward to multi-cloud chaos. So maybe you can elaborate a little. I know you did a little less cloud and a little more AI. But maybe you can talk a little bit about the cloud side of things.
100%. So part of our experience of why we actually developed a bunch of these was we looked at many organizations that had multi-cloud. So that was all in the problem piece of the slides, and I kind of like wanted to trim it a lot. But somewhere along these slides, I have hidden slides that just say that essentially many of the enterprises today are using multi-cloud for whatever optimization needs, right? Like sometimes you get a better deal on GCP than AWS or whatnot. The salespeople are really good. They give you like a bunch of solutions for free or something. And what you end up with that is you essentially end up with more dissected infrastructure. So not only is it more complex, it's actually more siloed, right? So they're more siloed, they're more disparate, and your aggregation can help, but your aggregation will not do proper detection. So the beauty of keeping things in like one premise or one cloud or whatnot, the beauty of unifying your infrastructure is when you run an EDR or an NDR or a CASB or whatever, configuration database management or whatever it is, whatever detection tool you're running, it's actually easier to tune the rules, right? So we talked about rules a little bit. It's actually easier to tune your sensors. It's a lot easier and more effective to tune a sensor like this on specific, essentially web requests that are coming in a certain format, right? Like I can easily tune this for a specific, let's say, web proxy or whatnot. It's not as easy if I have multiple web proxies. It's not as easy if I have a bunch of my users doing VPN, a bunch of them are doing SOCs 5 proxies, a bunch of them are not using the web gateway that we gave them, a bunch of them are working from home. Like it becomes more dissected. So there are solutions that try to unify, such as Zero Trust. You can use those, but ideally, the real solution comes at the aggregation layer. So let's get to the honest piece here. Your infrastructure would never be unified, right? It will never be unified. Ideally, you're counting on your security operations to somehow actually detect once you essentially aggregate everything. And I think that's a very big piece that people have discussed theoretically in academia. Like, should we push the logic to the edge? Like, should the sensor figure out what's going on? Like, should my EDR figure out the attack? Or should the core network, once we aggregate all of the intelligence, figure out the attack? There are benefits, there are pros and cons for both. You can essentially just run sysmon and d messages on your endpoints and never have any EDR detection there. And then through your core network, you might be able to send a few APIs to block certain actions and whatnot, essentially pushing all of your logic to the core. Or you can kind of like push it to the edge, but if you push it to the edge, you have that issue with essentially not unifying your detection, and it becomes less effective than you think. Because you would end up with some sensors that work well on Windows, but your sensors do not work as well, let's say, on Mac or Linux or IoT devices or mobiles, because you have maybe your MDM is not as good, it's not as well tuned as your EDR, and so on and so forth. And that just translates to the multi-cloud piece. Does that answer the question? Yeah, I appreciate it.
Hi, thanks for the presentation.
Thank you.
I just had a question whether, like, if you considered using threat modeling to improve 100%. And tune the accuracy of the, because I know you were trying to like map the attack flows, and I think it would be like specific, right, to the technology stack, you know, depending on what you're using.
That's an outstanding question. We did not play a lot with that because we wanted to make something that was a little bit generic. So we wanted the cyber knowledge encoding to be as generic as possible. So you can see that the place we actually encoded cyber knowledge was mainly in the large corpus. We added generic knowledge to the model, and then here we essentially based our knowledge encoding on the cyber graph data structure, the knowledge graph, which was, again, not customized. It was generic, coming from SciGraph, right? So we didn't try to nudge the model towards specific threat models, but that is an extremely valid idea to boost your model, because you already know you don't need a cybersecurity expert in your organization. You need an expert that is very familiar with, let's say, attacks that are many-to-one, because we get a lot of many-to-one. We're a CDN. I don't want all kinds of attacks to be very well understood. I want the many-to-one to be very well understood, or man-on-the-side attacks, because we're like an ISP or something. So you're 100% on the money, right to the dot. Like if I would build this within an organization and I really want to customize it beyond an internship project, 100%, I would eat all the threat models and I would change the Markov chain from a simplistic Markov chain that looks for all kinds of sequences to specific sequences that I know are probably going to hit based on specific MITRE attack technique sequences that I know are relevant to me, right? Because right now you can download a MITRE attack questionnaire from MITRE Ingenuity, and you can essentially fill up a little bit more information about your threat model, your organization, and it would tell you which techniques are actually more valid to you, right? What should you be looking for? And yeah, like you can very much customize the whole pipeline to very specific threat models. Question is right on the money. I appreciate you. All right, any more questions? Is it just too early for this? This should come after the drinking reception in the evening. All right, if there are no other questions, this was an absolute pleasure. I appreciate you guys. If you have any more questions or if you think of something, come up to the Arsenal booths. They're amazing, lots of great presenters, just like the summit, but they're kind of like more interactive, so you can kind of like get a lot more technical questions in and just like play with some software, and people are going to be super happy to kind of like walk you around. But I appreciate you. It was an absolute pleasure. Thank you, guys.